Hello, everyone. Did I start now? Okay. Hello, everyone. My name is Jianpeng Cao, and today my presentation topic is reinforcement learning for smart mobile factory operational in linear infrastructure projects. To begin with, let me introduce a little bit the concept of the mobile factory. So what is the mobile factory? Oh, sorry. Is it better now? Okay. So what is mobile factory? So it is a factory that can relocate as the project, especially the infrastructure projects, moves forward. It is like allowing the factory to control the production and on-site construction by moving to a closer location. And so it is easier to adjust the productivity and based on the on-site conditions. And also it's easier to handle the uncertainty happens on-site. So this is a small animations I created. So you see the factory can move to a different place. And so the question we're facing here is like, where do we locate the factory along the infrastructure project, and when do we move the factory, and where should we move the factory? And also, like in case of the production happened inside the factory, we also need to determine like what's the how many like production lines are we going to run inside the factory to determine the productivity rate. So for general like offsite construction, it is important to find a good synchronization between the site assembly and the factory operation so as to achieve the just-in-time delivery. However, like in practice, like the on-site and off-site management operation are usually managed separately. This is like especially like important for a mobile factory, as the mobile factory lacks the flexibility to balance the workloads across multiple projects. So in other words, here our assumption is like one factory only works for one project. And also the uncertainty of the project progress on site also need to be considered like in this case. And the consequence of a poor management might usually lead to excess inventory and delayed like delivery. To solve the problem, we look at the project scheduling approaches, and among which the reinforcement learning based approach deserves more research. So it is a probabilistic model which can handle the uncertainty and resource constraint and use machine learning algorithms for optimization. More importantly, the reinforcement learning based scheduling approach can generate dynamic schedule, which can adapt to like real-time status, project status, without the need to rescheduling every time when when there's no alignment to the planned schedule. The literature review indicates there's a lack of integration between the on-site project scheduling and the factory operational planning. Our research look at three specific gaps. The first, the mobility of the factory is usually not being taken into account, and the second, interaction between the factory and the logistic and site assembly, or we can call it the post-production process, is not well modeled. And the third problem is dynamic uncertainty in the construction task, especially the on-site construction tasks, are not well solved. So to solve the problem, we propose a reinforcement learning computational framework. So which contains like two major elements. Like one is the agent, which is defined as the factory here in our research, and the environment is the infrastructure projects. So the agent reacts to the environment by taking actions. So the action space is defined as the production, which can be characterized as the productivity rate, and also the movement or the idle state. According to so the agent makes a decision according to the current state. The environment will respond to the actions taken by agent by transition to a new state, and also provides the feedback to the agent as the rewards value. So here the state variable includes the assembly location, factory location, quantity of assembled parts, and the quantity of produced parts. The rewards function includes the project completion or milestone rewards, factory running cost, relocation cost, and transportation cost, inventory cost, under production cost, and the daily overhead cost. So let's look at the specific state during the process. The project is divided into the segments so that the current assembly location and the factory location could be indexed. And besides, the quantity of the produced parts and the quantity of assembled parts also are recorded so as to indicate whether the factory is like under production, overproduction, or provide on-demand production. And given the current state, like the factory and that is agent needs to determine whether to relocate to a new place or to continue run production or to just remain the idle state. And there's some assumption and when the factory is like moving or during the relocation process, the factory cannot run production. And the time interval to make the process, the time interval to do this decision making can be adjusted to multiple days or weekly. For this research, we choose a reinforcement learning algorithm called the proximal policy optimization network, PPO network, and this is like how we structure our network, which contains the policy network and value networks. The performance comparison between like a PPO network with other like reinforcement learning algorithms are not included in this research. And the model is like trained using the illustrative parameter values. So for example, if the relocation cost is low and the transportation cost is high, so we can see that the factory always move with the construction site. And you can see this is the action sequence of the factory, and there's a regular pattern shown in this action space, and that can be defined as the optimal like operational plan of the factory. And also from this chart, you can we checked the produced parts and the assembled parts at different time steps. So it shows like now the factory provides on-demand production. And in scenario 2, when we change the relocation cost high and set the transportation cost relatively low, we can see that in this scenario, the mobile factory might not be the optimal strategy. And therefore, the further exploration or application can be explored to determine the critical points, whether to choose a mobile factory or fixed factory for infrastructure projects. And similarly, you can see we find a regular pattern and in the factory's action space to be defined as the optimal operational plan, and also it fulfills the on-demand production in this scenario. And for the previous two scenarios, the reason why you see there's a regular fixed pattern because we define we use a deterministic productivity rate. But in case this is not really the case in practice. So and also another thing, we always use the model from the beginning of the project. So what if the project doesn't run as planned? So in this scenario, we introduce the variability of the assembly rate, and also we train the model with like different random states. So let's see if what if we have an overproduction state? Then the model suggests us to move closer to the site first, so as to shorten the transportation cost. At the same time, it consumes the inventory, and after the inventory is consumed, like at a certain time point, the factory will start running the production again. So to validate our solution, we use a BFA search, like BFA approach to explore the action space, and you can see from the results the solutions that, given by the reinforcement learning planners almost align with the solution given by the BFA search. So especially the first part of the solution. And in conclusion, our study contributes to our RL-based scheduling model for the optimizing the operation of mobile factory infrastructure projects. It is able to model the factory's mobility, interaction with logistic and site activities, as well as the dynamic uncertainty of productivity. And the future work will include the comparison with our model with other scheduling models, and also as well as the practical application and validation of scheduling model in a real-world project. This research is supported, is funded by the Swiss National Science Foundation, named Smart Mobile Factory for Infrastructure Projects, and it's collaborated with all of these institute and partners. And within this research, we also consider how the factory is designed so as to ease the disassembly and assembly of the factory, and to the development of the factory digital twin to monitor and control the production process, as well as the supply chain localization problem in the aspect of the economic and the sustainability perspective. More information can be found from our project website, and thank you for your attention.
Thank you so much.